Okay, so in 10 meter, you have 4,000 kVA. So in 1.75 meter, how many kV do you have? And you calculate like this. And the drop of the voltage from the starting point of the feeder until the regulator is a uniform drop. So 1.75 divided by 2. And then you need to add on to the remaining load, okay, which is 4,000 minus this, the remaining load 4,000 minus this, over the drop of the feeder. So the remaining load is 3,300, okay, as calculated. Take 4,000 minus this is 3,300. But when you calculate the remaining voltage drop, you calculate the remaining as a lump load, because now we are looking at the regulator. We are looking up until the regulator only. So up until the regulator, we have uniform drop, and the remaining loading of the feeder will be considered as a lump load on the regulator. Therefore, when we calculate the voltage drop of the remaining load, we just take 3,300 multiply L instead of L over 2. And therefore, the total voltage drop now is, when you sum up these two conditions and multiply K, and then you get this value. So the voltage drop entering the regulator will be this. So 1.0334 minus this will give me the voltage that is entering the regulator, which is this. Yeah. So as you can see, right, this is the graph that we want to obtain in the ultimate condition. Ultimately, when you obtain this graph, so initially 1.0334, and then because my regulator now is located at 1.75 meter away from the starting point, so the voltage entering the regulator will be this, okay? And then because the regulator has no R and X setting, remember that there's no R and X setting in the regulator, so the output voltage of the regulator will be back to only 1.0334. Okay, if can you imagine, if I have R and X setting, I can adjust this higher, so that allow the drop to be higher as well. So anyway, in this case now, the regulator is 1.75 meter away from the feeder, from the starting point of the feeder. So from here now, I need to calculate the remaining drop, and the remaining drop will be based on only 3,300 kVA, because in 1.75 I got 700 kVA already calculated from here. So the remaining will be 3300 kVA, and the remaining distance will be 8.25 meters. So again, the same thing, right? The same concept as this. Same concept as this. That is 3300 from the regulator until the end of the feeder will be based on a uniform voltage drop. Therefore, you calculate it like this. All right? Calculated like this. I'm just writing the formula so that you are based on the same logic. So 8.25 meter got 3300. So 8.25 got how many? So 8.25 is still 3300. So I put L equals to 0.825. You get 3300 multiply L over 2, which is the length of the remaining length of the distance, the remaining length of the feeder divided by 2, because a uniform voltage drop. And then going by the same equation, I take 3300 minus the remaining, which is 0 in this case. All right. So essentially, after the feeder, the voltage drop that we calculate is based on a uniform voltage drop. You take 3300 multiply L over 2, and that will be the voltage drop, 0.0528. So from here to here, you take this minus this, and then you get this. So if I move my regulator 1.75 meter down the feeder, but I don't do any active regulation, meaning my R and X setting is 0, then my voltage drop, okay, due to voltage drop, then my final voltage at the end of the feeder is 0.9806, and that still does not satisfy my condition, my requirement of at least having 1 volt plus bandwidth. Okay, therefore, I need to perform active regulation, meaning that I need to perform some sort of R and X settings so that this output regulator is somewhere higher over here, and when the drop happens, it is dropped above the required minimum voltage. All right, so I continue that in the next video.